open your weather app and scroll forward. Tomorrow is confident. 3 days out, still solid. By day 10 it's hedging. Vague icons, percentages that mean almost nothing. That fade isn't your app being lazy. It's the edge of something a meteorologist ran into by accident in 1961, and the strangest part is that scientists are still arguing about where that edge actually is. Edward Lorenz was running weather simulations at MIT on a Royal McBee LGP-30, a machine slower than a modern pocket calculator, working through a model with 12 variables. He wanted to re-examine a stretch of a run he had already completed. Rather than start the whole thing over from the beginning, he restarted it from the middle, typing in the numbers from his printout by hand. The computer held its numbers to 6 decimal places. The printout only displayed 3, so where the machine had been working with 0.506127, Lorenz typed 0.506, a difference of roughly 1 part in 10,000. The sort of discrepancy any scientist of that era would have dismissed as far too small to matter. He set it running and went for coffee. When he came back, the weather the machine had produced bore no resemblance to the original run, not slightly off. A completely different atmosphere. The tiny discrepancy had not stayed tiny. It had roughly doubled every 4 days, compounding on itself until it had swallowed the entire forecast. Lorenz's first assumption was that the computer had malfunctioned. It hadn't. What he had stumbled into was something far stranger. A system can be entirely deterministic, every single step following rigidly from the one before it, with no randomness anywhere in the machinery, and still be impossible to predict in practice. Determinism and predictability, which everyone had quietly assumed were the same property, turned out to be completely different things. And he wasn't working alone. The simulations were run alongside Ellen Fetter and Margaret Hamilton, the same Margaret Hamilton who would go on to lead the team that wrote the flight software for Apollo. The code that helped put humans on the moon, and the discovery that the weather cannot be pinned down, came in part out of the same small group of people working on the same borrowed machine. Weather turns out to be the ideal system for this to happen in for 3 reasons. It's non-linear, meaning effects don't scale neatly with their causes. Every hour of a model is built directly on the hour before it, so an error doesn't merely persist, it compounds. And we can never measure the starting state perfectly. There is no weather station on every square meter of ocean. There is always a gap between the atmosphere and our picture of it, and that gap is where the error is born. Lorenz eventually put a number on it. In a 1969 paper, he modeled how quickly those errors grow, and concluded that skillful, detailed forecasting runs out somewhere around 2 weeks. That figure escaped the academic literature and became one of the most repeated facts in all of science. You have almost certainly heard it. It is printed in textbooks, quoted in documentaries, and treated as settled. Then, in 1972, he gave a talk with a title that would outlive everything else he ever did. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? It became the most famous metaphor in modern science, and also the most misunderstood. Lorenz was not claiming that a butterfly causes tornadoes. He was making a much sharper point. If a disturbance that small can matter at all, then perfect long-range prediction is permanently off the table. The field's response to this was genuinely clever. If you cannot know the starting conditions exactly, stop pretending that you can. Modern forecasting runs the same model dozens of times over, each from a slightly different starting point, and then looks at how widely the results spread apart. A tight cluster means confidence. A wide scatter means the atmosphere is in a mood. That 70% chance of rain on your phone isn't vagueness. It's the honest output of a system that has stopped claiming a certainty it doesn't possess. And here is where it gets genuinely interesting, because the 2-week wall is no longer settled science. The 1969 model that produced that number has come under serious criticism. It leaves out major atmospheric processes, which means it may never have been the right instrument for measuring the real atmosphere's limits in the first place. And this critique doesn't come from outsiders throwing stones. Lorenz himself came to acknowledge the model's shortcomings. Recent work has pushed in the other direction entirely. Machine learning weather models have cut 10-day forecast error dramatically and are demonstrating real skill well beyond 30 days, far past where the wall was supposed to stand. Separate analysis suggests that improving our initial measurements by a factor of 10 would extend reliable mid-latitude forecasting out to roughly 15 days. The famous limit, it seems, may have been partly a measurement problem wearing a mathematics problem's clothes, none of which rescues infinite prediction. Sensitive dependence on initial conditions is real, and it has been confirmed in systems far beyond weather. Some horizon genuinely exists. What remains unresolved is where it actually sits, whether we have been standing near a fundamental boundary of the atmosphere itself, or merely at the edge of how precisely we can currently measure it. Those are two very different claims about the universe, and the field has not settled which one is true. A man rounded a number, went for coffee, and came back to find that the weather had changed. 60 years later, we still don't know exactly how far ahead the universe will permit us to see. Only that the answer isn't infinite, and probably isn't 2 weeks either. Does it bother you that some things may be unknowable in principle, or is that the more interesting universe to live in? Let me know in the comments. New discoveries unlocked daily. Subscribe so you never miss one.